Hello everyone. Today we will cover section 9.2 vectors. Okay. In nature, there are two kinds of quantities. One is called scalars, the others are called vectors. So, section 9.2 vectors. So scalars. What are these scalar quantities? Things can be described only by some real numbers. Once you introduce units, there is no direction inherently in this concept, like temperature. Okay, there's only hot or cold, right? Not north, south, east, west direction in it. Mass of an object, also scalar quantity. Okay, once you introduce a unit, you just need real number to represent, to describe. That's it. It's one. There are many quantities, right? Scalar quantities. On the other hand, there are vector quantities, which requires not only how large it is, but also in which direction it is acting to describe that quantity fully. So, for example, force. It's not enough to know how strong a force is to predict the effect of the force on an object when you apply the force. Right? Not only how hard it is, you have to know in which direction is applying the force to predict the future location of an object, right? When it starts moving, accelerating. Force, velocity. Not only how fast you're going, but also in which direction you're going. You need to know both, right? Acceleration. Or displacement. So what is displacement? The change in location is what we call displacement, change in location. So, so this will be, I would say, our prototype of a vector. We introduce vector operation using displacement and then find that operation among vectors can be extended to any kind of vectors, first of all. So, let's say you're moving an object from this initial point to Q, terminal point. Okay? Now, then we call it PQ, from P to Q. So, this displacement vector describes change in position of an object from this point P to the terminal point Q. Okay? And also we can use this arrow connecting initial and terminal points, right, to describe. So, a lot of times we use arrows, right, with arrowhead to describe a vector. Okay, let me check the recording. Okay, so now in vectors, two vectors. What does it mean by two vectors are equal? Okay, two vectors u and v, two vectors a and b are equal. IFF, if and only if they have the same direction and same magnitude. Magnitude is the size of the vector, how large it is. So in displacement vector, the magnitude of the vector will be the distance between those two points, right? Direction in this case is more or less northeast direction. Now, two vectors are called equal as long as they have the same direction and same magnitude. Even if two vectors are describing same kind of quantity in different locations. For example, let's think about it. Let's say this morning, 8 a.m., Bakersfield, California weather station recorded wind blows from northwest 10 miles per hour. And Fresno weather station at 8 a.m., they also recorded a wind velocity from northwest direction 10 miles per hour. Now what would you say about two wind velocities in two different cities? Both from northwest direction, both of them 10 miles per hour. And you would say, somehow two cities had the same wind velocity at that time, 8 a.m. today, right? Because both wind velocities have the same direction and same magnitude. Same magnitude, 10 miles per hour, right? Two vectors are equal as long as they have the same direction and same magnitude. Even if those two vectors are describing situations in different locations. So it is not important to where you draw the vectors, as long as your vector have the same direction and same size. Size means magnitude. They are equal. So if I draw this, let's say this is exactly the same magnitude and same direction. Then this is, okay, same size and same direction, then they are same vectors. So an example. A. Let's say two displacement vector. P to Q. Your P is, let's say 1, 2. Q is 3, 6. And RS is going, let's say this is 3, -2 to S 5, 2. Two different location displacement. One is change in location from 1, 2 to 3, 6. The other 3, -2 to 5, 2. This one, the direction is from 1 to 3. You have to move 2 horizontally, 4 vertically. Here, also 3 to 5, 2 horizontally, and 4 vertically. So they should have the same direction and same magnitude. The distance will be same, right? Square root of 2 squared, 4 squared. Square root of 2 squared, 4 squared. So they are equal vector. So in this case, PQ vector equals RS vector. What about this case? This is vector C, exactly parallel, same size, opposite direction. Same. Opposite direction is not same direction. They are parallel but not same. So in this case, they're not equal vector. All right. So this is the equality of two vectors. What about some operation? Let's say you have a vector A. We want to define constant multiplication of vector. So what does it mean by 2 times A? Twice as large as A. Well, we want to mean that twice as large but same direction. Then that is 2 times A. Okay, that's how we want to define. Or 3A will be same direction, 3 times as large. Okay? Minus 1 times A, we want that to be opposite direction, same size. Okay? Opposite direction, same size. Therefore, minus 2 times A should be opposite direction, but twice as large. Okay? So that's how we define scalar multiple of vectors. Alright? Now, this one, we write it just minus vector A. Additive inverse of vector A. Well, we'll define what addition of 2 vectors is. Okay, so that's constant multiplication. Scalar multiple of vector. What about vector addition? Vector addition. Okay, again, we will start with displacement vector. What is the net resulting effect when you combine 2 displacements, like displacing an object from P to Q, this is PQ vector, followed by Q to R. So we want to define what it means by addition of 2 vectors. 2 displacement vector. The resulting effect would be a displacement from P all the way to R, isn't it? And you could say that R to S is a net resultant effect when you combine these 2 displacement vectors. Alright? So we will define vector addition like this. Even if those vectors are not displacement vector. So if you have a vector U and then draw vector B, V like this, successively back to back, then U plus the V vector will be defined as this vector. Alright? So if you want to add 2 vectors, you just put 2 vectors back to that position, and then you connect from the very beginning to the very initial point of the first vector you're adding to the terminal point of the second vector. Then it'll be vector sum of the 2 vectors. Alright? That's how we define 2 vectors. Now, why do we define vector addition like that? Because we realize that in nature, so-called vector quantities, when you combine 2 vectors in same kind, combine it, the resultant effect is actually same as a vector we define addition like that, right? So we are inspired by the observation of how nature works, right? This is the way 2 forces are acting. So let's say you apply force, one of them this way, F1, and you apply force over here, applying F1, F2. Then what would be the net resultant force? Well, then you want to draw F first over here. Okay. So we learned that these 2 vectors are not drawn in this back-to-back fashion. So we draw F2, starting here. We learned that as long as you draw same direction and same size, they are same vector. So this F1 followed by F2, therefore your resultant vector. This is F1 plus F2. So the way find some of the two vectors this fashion is called triangle law of vector addition. Call it triangle law of vector addition. So this just shows how we do this. Okay? You just draw two vectors back to back. Okay? Now, so there are slightly different way of describing some of two vectors, but essentially same thing. Let's say your two vectors are not drawn back to back fashion, but sharing the same initial point, like vector u and vector, say vector v. Now, they have the same initial point. Then, in order to add two vectors u and v, I have to draw vector v starting from here back to that fashion. So let's say vector v. Now, what happens if I just draw vector v over here? That means that this is same direction and same length. So if I connect this, it'll make a quadrilateral where these two vectors represent same vector. That means same direction means at least it is parallel, they are parallel, and same magnitude means that congruent, same length. So when a pair of opposite sides are parallel and congruent, this quadrilateral should be parallelogram. Because it's parallelogram, the other pair of the opposite sides are also parallel and congruent. So that vector has to be vector u. Alright? If you draw vector v here, then it has to be vector u from that simple geometry. So, u followed by v, that is precisely vector u plus v. This is u plus v. Okay, u followed by v. Here, v followed by u. Same thing, right? So u plus v is actually v plus u. Okay? So in the end, what we need to learn here is that if two vectors are drawn from the same initial point, you just draw a parallelogram out of it. Then the diagonal from the common initial point to the opposite point, that diagonal will give you, diagonal vector will give you sum of the two vectors. Which is equivalent to this. I mean, we just got this one from back-to-back drawing, right? So this, this method of getting sum of two vectors is called parallelogram law of vector addition, which is essentially same as triangle law of vector addition. Okay? All right. That's how we define vector addition. So, with vectors, we can think about two operations. First, constant scalar multiplication. The other, for constant multiplication of vector. And the other is vector addition, addition of two vectors. In real number case, and also zero vector. Zero vector. We use number 0 and arrow. So it is a vector with magnitude 0. Magnitude 0. Magnitude 0 is 0, nothing. When you have a 0 force 0 vector, a force vector is 0 vector, means that you don't apply any force. So it doesn't make sense to talk about direction. So 0 vector works just like number 0 in real number addition. So vector v plus 0 vector, or 0 plus v vector is just 0 vector. Okay? So 0 vector is identity in vector addition. Okay? Now, in real number system, subtraction of two numbers was defined as, actually, a minus b was defined as addition of a and additive inverse of b, right? So now same thing for vectors. Vector subtraction can be defined the same way. So definition. Vector A minus vector B is defined vector A plus minus B. Minus B is the opposite direction of B, same magnitude, alright? And this is actually additive inverse vector, additive inverse of vector A, because the A followed by negative A come back to where you started, right? So if you define, think about it. A minus A can be drawn, yeah, minus A is over here, minus A, that's the opposite direction, the same magnitude over there. If I draw A starting from here, you come back where you started. So if you do back to back, so-called triangle law, even though they don't make triangle, but you know, then, right? So this is additive inverse of vector A. Well, the reason why we wrote this way is because we already knew this would happen. Okay, so just like the number subtraction, vector subtraction is defined as addition with additive inverse of a second vector. Okay? So, okay, let me check the recording. Okay. All right, then geometrically, how do we describe? Let's say this is vector, let's say vector A, vector B. Then, in order to do A minus B, I need minus B here. Vector B. So minus B will be opposite direction, same size. Alright? So something, okay, minus B. This is vector A. Vector A. So A minus B is A plus negative B minus B. So you have to add these two vectors using parallelogram law. You can draw parallelogram. Now, if I draw A over there, what happens? Let's say this is vector A. I draw A over there. So, same size and same magnitude, so parallel, congruent, so it's going to be parallelogram. Okay. Then, I don't need this actually. Now, if you connect this, what is it? This is B. This is a parallelogram. These two are parallel and congruent. These two. But this is also parallel congruent. So that means these two are parallel congruent. It makes a parallelogram. So this will be same as this vector, right? So that means now we focus just this way. When you have a vector A and B drawn from an same initial point, in order to get A minus B, yes, originally you have to draw minus B vector and then add vector A and vector minus B. But you just can get it right away by connecting the tip of the subtracting vector toward the tip of the subtracted vector, right? So this is what you get. So if you have, let's say in different direction, let's say vector A is over here and vector B is over there. A minus B, now according to this, starting A minus B, then starting from the tip of the subtracted vector toward the tip of the subtracted vector. Alright? That's how you can get subtraction of two vectors quickly. So for example, now let's make a connection with this one and what is it? Displacement, for example. So let's say P to Q, P to R. Then look at this. PR plus RQ equals PR RQ is back-to-back addition. So what do you get? PR RQ is PQ, isn't it? Okay. Now you add PR, subtract PR from both sides. And what do you get? RQ is PQ minus PR, right? PQ vector minus PR vector, see, is R to Q, R to Q. Alright, same thing from the tip of A to tip of A, tip of B from tip of A, from tip of the subtracting vector toward the tip of the subtracted vector, R to Q. Alright, same thing. Okay. Now so far we introduced vectors geometrically using arrows, direction, size. But if we have to draw two vectors to add or subtract vectors to add, draw two arrows and then find out the diagonal direction, then this is so analog, right? It's not easy to make a exact value. Still, you can do it using law of cosine, law of sine stuff, but it's going to be much harder. There's another way of describing vectors, direction and the magnitude using components, right? More of a digital approach, you would say. So for example, so when you have a vector, let's say v is given, how do we describe the direction? Well, one way to do that is this. From the initial point to the terminal point, horizontally, how much do you have to go? Let's say A. From there, how much do you have to go vertically from there? Okay? In that case, you say angular bracket AB. We call A is x component. Let's say the horizontal direction is this is x coordinate. This is y coordinate. Alright? Obviously. When you have this. Okay? This is x component of vector v. This is y component of vector v. Now, we learned that if two vectors have the same direction and same magnitude, those two vectors are considered same, equal. Then I can draw the same vector starting from the origin, going by A and up by VB, which means over here B. If P is a point whose coordinates is AB, right? Origin 0, 0. So that means if your P is the point AB, and obviously the origin is 0, 0, then the vector V is OP vector. Alright? So the OP vector equals here V. So if you draw a vector from the origin, initial point at origin, then xy coordinates of the terminal point is exactly xy components of the vector. Alright? That's what you see here. Alright? So these are components. Now this is for two-dimensional case. Three-dimensional case, we can do the same thing. Actually, you learn vector components and all this for two-dimensional vector in math analysis already, or pre-calculus. Math analysis in high school, which is equivalent to pre-calculus in college. So what about three-dimensional vectors? Let's say, now, let's see, draw vector from origin to P, which is A, B, C. That means let's say this is A, B, and C. Right? Horizontally, you have to move by not horizontal, along the x direction, and then along the y direction, you have to move by B, and then along z direction, you move by C. So that means your terminal point is ABC. Then OP vector has x ABC components ABC. Alright? So this is x component, y component, and this is z component. Okay, component of the vector. Okay? Oh, by the way, so in this case, your magnitude, when you have a vector like this, vector component AB, then magnitude, we use absolute value sign for magnitude. Well, some other textbook they use double bar, same thing. Magnitude, it's just length of this hypotenuse in a right triangle with legs AB. So square root of A squared plus B squared. Okay? Same thing here. Now, if you have connecting from A, which is x1, y1, z1 point, let's say B, doesn't look parallel, slightly up, so hard to draw. A, let's say B is x1 plus A, y1 plus B, z1 plus C. That means from AB, you have to go by A, B, and C along the direction. Alright? Then AB vector will be same as this OP vector, which is component ABC. And in that case, alright, magnitude of AB is square root of A squared plus B squared plus C squared, which is the distance between these 2 points, right? Magnitude of displacement vector. Alright. So, in the end, this A is this x coordinate minus this x coordinate. How much did you move along x direction, right? So, if you are given 2 points, if point A is x1, y1, z1, and point B is x2, y2, z2, and if vector v equals displacement vector from A to B, okay, then your v has to be, oh, just write it. Then vector from A to B will be just terminal point component is x2 minus x1, y2 minus y1, z2 minus z1. Okay? And also, vector equality. If vector u is ABC. Okay, no, let's say x1, y1, z1. As a vector, vector b has x2 let's see. If 2 vectors are given in component form, we call it component form, then vector u and v are equal if and only if each components are equal. Right? 2 vectors have the same direction, then if you draw 2 vectors starting from the origin, they will end up at same terminal point, right? So components must be same, obviously. Okay? So, that case. Now, we want to learn how to get those vector operations result in component form. For example, let's say vector u is ABC. ABC. What is opposite direction? Opposite minus u should be, negative A, negative B, negative C. Alright? Okay. Let's write say vector u here. Opposite direction. So u is a, b, c. Then minus u is going the other way around, so minus a minus b minus. It has to be opposite direction, same length, going here. What about twice as large? 2u. Then it should be 2a, 2b, 2c, right? It's obvious. Two-dimensional and three-dimensional, you can actually show this one easily. Therefore, if u is a, b, c in component form, then constant scalar multiple ku will be ka, kb, kc, all. And also, magnitude of ku will be k times magnitude of u, but when k equals a negative number, you have to take absolute value, right? You can easily see this, all right? So, let's do some examples after I check some PDF. So here, let's say example 3. Let's say point A is 1, negative 2, 3, and point B is 3, 1, 2, and let B equals AB vector. Find the component form of A, V, B, 2B, C minus 3 times B. Okay? Solution. Well, vector B as from A to B, we learn this. This minus this. So 3 minus 1, 1 minus negative 2, 2 minus 3, which means 2, 3, negative 1. Okay? Well, what about 2b? 2b. 2 times this. Just multiply your each component by that number. So 2 times 2, 4. 2 times 3, 6. 2 times negative 1, negative. That's it. C. What about negative 3 times b? Well, negative 3 times 2, 3, negative 1. Again, you just do the same constant multiplication of each component. Negative 6, negative 9, and positive 3. Okay? Alright. Now, so constant multiplication can be done in component form really easily, right? K times vector u, just k times each component. Then you're going to get component form of a scalar multiple of a vector. What about vector addition in component form? I'm going to give you this. Let's say vector A. Let's say vector A is A1, A2. Vector B equals B1, B2. So if I draw vector A from here, this is A1, A2. Now I draw vector B starting from here. This is vector B, which means this is B1, B2. So if I draw from here, that x coordinate should be A1 time plus B1, right? just projection B1 on top of A1. This is A2 here. What is it? A2 plus B2. Right? Now, A plus B, this is A plus B. Oh, no. What am I doing here? That's not the origin. Origin is starting from here. This is A plus B, right? So, this is the point where xy coordinates A1 plus B1, A2 plus B2 point. Let's see, P. Oh. So what do you find? If A vector is A1, A2, B vector is B1, B2, apparently A plus B, some of the two vectors component form can be obtained by just adding A1 plus B1, A2 plus B2, isn't it? Right? This is it. Probably this is the most important reason why we prefer component form to geometrical representation of vector. Because we can get some of the two vectors right away by just adding component-wise addition. X component A, Y component A, that's it, right? No more cosine laws, when you draw this vectors, to get this, you have to use cosine laws to get this angle and this direction, sine law, cosine law. We don't have to do that if you are given vectors in component form, all right? Likewise, as A minus B vector will be then A1 minus B1, A2 minus B2. Very easy. So, two-dimensional case same, three-dimensional case is same. If vector U is U1, U2, U3, and vector V has V1, V2, V3, all right, three-dimensional vectors given in component form, then U plus V will be just adding X components, Y component added, and Z components are added, U3 plus V3. All right? If you want to subtract, then subtract. Okay? This is the reason, the most important reason why we use component form of vectors. So, this is, let's say, example 4. If vector A equals 4, -1, 2, and vector B is 1, 2, 3. Find magnitude of A plus B, A minus B, and 2A minus 3B. Okay? That's easy. What is it? So, magnitude of A is square root of X component square, Y component square, Z component square. So square root of 16, all right? And 1, 4, and square root of 21. What about A plus B? Just add 4 plus 1, minus 1 plus 2, 2 plus 3. What is it? 5, 1, 5. Okay? What about A minus B? 4 minus 1, negative 1 minus 2, 2 minus 3, so 3, negative 3, and negative 1. Okay? Finally, 2a minus 3b. So 2 times this, 4, negative 1, 2, minus 3, 1, 2, 3. Well, multiple by 2. 8, negative 2, 4. Minus 3 times this, 3, 6, 9. Now subtract 5, minus 8, minus 5. Okay? So this is the end of the actually first part of section 9.2. Alright, second part will be done in separate video. Okay, thank you.